Hi everybody. So today I want to provide you with one more module to go along with Lecture 1 since we did not have time to go over it in class. That is robustness. The idea behind robustness is it's something you want to have incorporated into your code. And when we say that your algorithm is considered to be robust if it completes successfully for all reasonable inputs. So what do we mean by that? The best way to talk about this is to show it in the context of an example. So let's talk about the quadratic formula. We all know that if you write out a quadratic equation, ax squared plus bx plus c equals 0, you can solve for the roots of x as minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. So what you could do is write a function where you have x as a vector, the output of the function, and we'll call this function, say, quad form, just to give it a name, and the user would provide a, b, and c. So the user provides a, b, and c, and what they get out of it is a vector x with the roots. All right, so there's an issue if you do the naive approach where you just simply toss a, b, and c into this equation here to get your roots in x. The issue, of course, is what happens if the user puts in a of equaling 0. So it turns out there's another one here, but we'll focus on this first. So what if the user provides a equals 0? Well, then you get a NaN, or not a number, designation from MATLAB. If you were to do this in MATLAB, that obviously is not a successful completion of the quadratic formula. Really what should happen is your quadratic equation would, instead of being ax squared plus bx plus c equals 0, it reduces down to bx plus c equals 0, or x equals minus c over b. So what you would do then is provide an if statement in your code, which looks something like this. If a equals 0, then x equals minus c over b. And then you can have an end statement, or you could have an else statement and dive into what happens when a is not equal to 0, which means you would solve for two roots in that case. But there's a second issue that could arise as well, something that's a little more subtle. That second issue is, what if it turns out b, or rather b squared, is much, much larger than 4ac? So let's take a look at that case here. So we'll say b squared minus 4, let's do it this way here. B squared much, much larger than 4ac. So the quadratic formula up above, to solve for the roots in x, I'll just write it again here. So minus b plus or minus the square root of b squared minus 4ac all over 2a. So what I'm going to do, if b squared is much, much larger than 4ac, that means that everything inside of here is approximately equal to b, roughly. It's just going to be a value of b, but slightly off, so slightly smaller than b. So what that means then is, if you look at we're taking the positive part of this numerator here, so we get x on the positive side is minus b plus b over 2a. Again, remember this value of b here is just a little bit off. So what we get are two very, very similar numbers, and what we get then is a subtraction of these two similar numbers. What we get then is a loss of significance, which we talked about in the second module today. So the accuracy is going to be bad. So how do we get around this? Well, if you have a case where b squared is much, much larger than 4ac, let's take a look then at, again, this positive side of this root here. So we get minus b plus square root of b squared minus 4ac over 2a. And we're going to multiply it by minus b squared minus 4ac on both the top and the bottom. We're going to use the difference in squares to achieve our goal here of avoiding our loss of significance. So using the difference in squares, we get b squared minus 4ac up top. In the bottom, there's 2a comes minus b minus square root of b squared minus 4ac. This can be simplified, obviously. So the b squareds in the top cancel out. So that goes away and that goes away. So we're left then in the numerator just 4ac. And in the denominator, let's take out the minus sign up front. So it's minus 2a times b plus square root of b squared minus 4ac. We can simplify it further by dividing 4 divided by 2, getting rid of the a's. So what we get then is minus 2c over b plus square root of b squared minus 4ac, like so. Now you can see that whereas in the numerator before we had a minus sign, right? We had b minus b essentially, or something close to b minus b, and that gives you loss of significance. Now in the denominator, we now have a plus sign. So this addition means that we do not have a loss of significance. So a robust algorithm then would have if statements that would look at all possible areas where you could have issues with solving your particular algorithm here. So, for example, again, with the quadratic formula, you wouldn't just use this. You would do a check ahead of time. You would say, well, what happens if a equals 0? Then you have an if statement for that. And then maybe after that, you can say, well, what if b squared is much, much larger than 4ac? Well, then you use this formula here to get one of the roots. And so that's how you would do it. And then if neither of these two conditions apply, then you can just do the straight solve. And that way, no matter what you have for any reasonable inputs for the quadratic formula function, you'll get roots that are accurate.